who is a well-known scientist and the researcher in the field of pressure, thermal, and many other fields. As we are all aware,
You are muted, sir.
yes, yes, sir. So I'm just, we are all aware that is a awardee. It's a great place, done the very good job in science and technology in India, but also at the international level. We have with us our Honorable Director Sir, Shri B.N. Dikshit Sir. First of all, I would like to request Shri B.N. Dikshit Sir to kindly speak 2 words and inaugurate the workshop so that we can later on go towards request Dr. Sanjay Yadav Sir to kindly to speak and give his lecture. Dikshit Sir, please.
Uh, First, I will congratulate that you are having the different topic on different weeks, so the scientific community may increase their knowledge in the different subject. Heat is also one of the very important topics. It is not only related with the measurement factors, but it is related with the various industrial factors also, that how the mining fields may be maintained, how the LOIs can be detected. So many things are there. A lot of people are losing their life. So many precautions are being made. So heat is a very important thing. I hope that apart from the measurement of the heat, so many other values that on these factory issues, how the heat environment may be maintained and the people's safety may be maintained, that also should be discussed. With these very words, I congratulate you, and I say my whole good words to Dr. Sanjay Singh Yadav and other participants to speak uh, their presentations in the very light manner. Thank you, sir.
Thank you very much, sir. Thank you for your kind words. And certainly, sir, these type of workshops will help our Indian people, our Indian industry a lot to understand the new things which are happening in the field. And we have with a great scientist, Professor Sanjay Yadav, sir, who has a lot of experience not only in India at the international level. He has done this research and development at in different levels, maybe in PTP Germany, Japan, and many other countries. So, sir, I would like to request who is actually the most important part is he is an sir Asia Pacific Metrology Program awardee from India. I think that he is the only one who has obtained this award in science and technology from India, from National Physical Laboratory. Sir, now kindly I would like to request you to kindly speak. I am very sorry that our initial 5-10 minutes we have wasted due to some technical problems. Sir, please, you start, sir.
Good morning to all of you, and thanks Ashutosh ji and Dikshit Saab. Dikshit Saab is always our mentor. He has been so kind all the time. So thank you, Dikshit ji, for your kind words. And I also join with you to congratulate Shri Ashutosh ji to conducting this regular training program, or you say workshop or webinar continuously so many days. And I am among a few which are coming repeatedly. So I have attended a few, and I have also taken as a speaker in a few of the seminars. So it is always my privilege to have among you and share whatever little I know. It is always my pleasure to share with my colleagues and participants. So today's seminar, I will be speaking in a little bit in a series of lectures. First lecture is basically some terminology and which are very important related to pressure measurement. But these terminologies are very important before understanding the advances in metrology. Slide is not moving actually. I think I have to redo it again. Hello.
Sir, any issue, sir?
It's not moving. Slides are not moving.
Again share, sir. Please share again.
This presentation to you, you can also run this presentation from here.
Sir, it is moving here now.
No, sir,
No. Not running. Yeah. Okay, I have to do a different way. So now we'll go for the basic terminology. For this basic terminology, one has to understand this beautiful document that is called International Vocabulary of Weights and this general terminology in metrology. So whenever you go for the measurement, then you have to have one word that is measurable, and we call it quantity. So that is quantity. What is quantity? It's basically attributes of a phenomena, body or substance, that may be distinguished qualitatively and determined quantitatively. So that is the quantity. So when we have the quantity, then we can quantity, then we can have some example like a length, time, mass, temperature, electrical resistance, pressure, vacuum, flow. These are the quantities, and then we can have, when we have the quantity, then we have the value. So any quantity you have to express in terms of the value or magnitude of a value. So that's why this document is very beautiful. Now you have the quantity, you have the value. Then you can see the examples 5.34 millimeter or 5.534 centimeter or kilogram, mole, and so on. So after this quantity and value, one terminology comes to the true value. So of a quantity value consistent with the definition of a given particle quantity, you must have some true value. True value is not attainable, but you always try to reach near to the true value. Then we have conventional value. That's why you go to some near to the accepted value. So then you have to have some conventional value. Then we have several example measurement. Then when you have the quantity, then we have the value, then we have to start measurement. So what is measurement? A set of operation having the object in to determine the value of a quantity is measurement. So now you see each and every terminology is connected. First, I told you the quantity, then I told you value, and then on measurement. You see in the definition of measurement itself is the value and quantity. So this document is very, very beautiful. I will request you, all of you, to go through after my lecture. You will enjoy reading this after this lecture, because I am giving you the beauty of this document. So again, in different terminology, you can say that process of determining the value of some quantity in terms of a standard unit is called this measurement. So, and when we have the measurement, then we need measurement process or measurement method. So now, after measurement, you have the process and method. So this is another continuation. And when you have the process or method, then you make measurement. So how you can make measurement? It can be a single measurement. Then you have a repeated measurement to increase your confidence in the measurement. Then you have the estimating population parameters. Can't make an infinite number of measurement, because the system being measured should be financial and technically viable according to your investment also. So that's why you cannot make continuously infinite measurement. So you have to have certain number of measurement. Then after making measurement, you need to what to measure. So what to measure is called measurement. So quantity, value, measurement process, method, technique. Now comes the term measurement. So particular quantity subjected to measurement is called measurement. So in 20 degrees centigrade, measurement is the temperature. So you can go continuously in this way. Then when you are making measurement of a particular measurement, there are certain influencing quantities. So that influencing quantity affects your measurement. So accuracy of your measurement depends upon the influencing parameters. So example, temperature of a micrometer used to measure length, and frequency in the measurement of the amplitude, alternative electric potential difference. And in a metallic length measurement, you can have a variation of temperature and environmental conditions. And after all this measurement process of a measurement, then you obtain what? What you obtain? You obtain the result of the measurement. So value of attribute to a measurement obtained by a measurement. So that is the result of measurement you can get. Like it can be through the indication. You can have uncorrelated result, then you have correlated results. A complete statement of the result of a measurement include information about the uncertainty of the measurement also. So uncorrelated result of a measurement before any correction is uncorrelated of a systematic error. And when all this correlated result of a measure after corrections are applied, all the errors, then you have the correlated errors. One terminology, accuracy of measurement. So closeness of agreement between the result of measurement and true value. Understand the implications of accuracy and measurement. Accuracy is purely the qualitative concept. The term precision should not be used in place of accuracy. Precision is basically the characterization of the standard deviation. So accuracy is the characteristic of the instrument, but uncertainty is the characteristic of the measurement. Please understand that logic. So when you have all this, you need to repeat the measurements, and you have to have the repeatability of the measurement. So repeatability of the measurement is nothing but you can characterize it by the standard deviation. So closeness of the agreement between the result of successive measurement of the same measurement carried out under the same condition of measurement is the repeatability. Then we have the repeatability contents include the same measurement procedure, same observer, same measuring instrument used under the same condition, same location, repetition over a short period of time. So short-term repeatability, there is a long-term repeatability. When it is the long term, sometimes it is called reproducibility if certain parameters are changed. So reproducibility is the closeness of the result of the same measurement carried out under different condition, different instrument, maybe different or same, maybe different same or different operators, different locations. So this is the reproducibility of the measurement. So, if you see this particular pressure gauge graph, you will see the repeated measurement over the years and the behavior of the gauge. So, you can also check the average. So, over the year, you can find there is the behavior of the gauge are same, but there is a little bit away. So, that is the drift in the measurement. So when measurements are in unidirectional, then it is called the drift. But when measurements are not in unilateral direction, and sometimes it is down, sometimes it is up, it becomes the part of the scattering, means dispersion. So that becomes the part of the measurement characteristic. Then change the conditions for repeatability may be principle of measurement different, method of observer, measuring instrument, reference standard, location, condition of use, and of course time. So in key comparisons, you will find that reproducibility of the measurement is made at a different location by different laboratory on same instrument. Then comes the very important term is resolution. So it's the smallest difference between indications of a display device. This is another important characteristic of a measuring instrument. So now you see this particular slide, you will find the different resolutions of the gauge in digital format and also in analog type. So smallest measurement you can make using this instrument is the resolution, but how you can take this quantity in terms of the uncertainty. So this formula you can use R is equal to SSI divided by F. R SSI is what? Smallest scale interval. So smallest scale interval and F is the frequency, and frequency is normally dependent upon the user. You can, if you are a perfect user, you can divide it between 2 to 10, but normally it is safer if you divide it smallest scale interval by 2, but there is no restriction. Standard say you can divide it by 10 also if you are expert and you can resolute resolution. So that is a clear thing. Then uncertainty is never resolution. So please understand, uncertainty and resolution are different quantity. In a particular example, you can say resolution is 5 degrees centigrade here, and in another example is resolution is 1 degree centigrade, and but uncertainty is you can see the by scattering of the results. Drift I have already explained, unilateral and multilateral direction. You can have a drift definition. And then sensitivity of the equation, sensitivity of the equipment is the characteristic of equipment sensing the minimum change in the instrument. So sensitivity may be different from the resolution. An instrument can be more sensitive than resolution, because resolution is assigned by the manufacturer. That's why standard says you can resolute resolution for the evaluation of error by dividing 2 to 10 according to your capability or type of expertise available. So calibration, I will take later on. Yeah, definition wise it is okay. Calibration comparing the reading of an instrument when it is exposed to known artifact of a condition. Either the instrument is adjusted to read correctly or table of correction, or this which is basically a method by comparing measurement taken by measuring instrument against the standard whose measurement uncertainty is known and is traceable to national or international standards. So another terminology in your case is verification. So most of the work involve verifying the instrument, oblique probe, etc. specification. This is not a calibration since correction, etc. are not supplied in verification. Since equipment sent to the field is within specification but may be anywhere within the specification. So this is example of that verification thing. Uncertainty of measurement, I have explained. So if you want to understand by this bullseye experiment, you can see the particular left-hand side, you can see the low accuracy and high precision. But this middle one is, it is medium accuracy and low precision. And similarly here, high accuracy and high precision of the target value. So that way you can understand. Another example is given here. Then reference conditions, you have to maintain condition of the testing performance measuring instrument. Then error. There is a difference between error and bias. Result of a measurement minus a true value of the measurement. So please understand this. Bias is not always the error. Bias you have to correct. Measurement error you have to apply. Relative error, and then accuracy of the instrument. Then we have permissible error. You are more familiar with this permissible error and limit of permissible error. So in nutshell, the closeness of the experimental mean value of true value is basically high accuracy equal to small systematic error, and the precision is degree of scattering in the results. So precision is the closeness of agreement between independent observation, and this is accuracy is closeness of the value with the assigned value. Adjustment. So sometimes you have to adjust your instrument before the measurement, but there is implication how to make that. So this slide I always show field adjustment. You try until you can apply. Don't apply. Just don't apply. And an adjustment in the field remove all traceabilities. So that is my point of view. If it is out of specification, remove your instrument, get it calibrated, and then again do experiments. So field adjustment is not allowed until and unless some this regulatory requirement. So after the adjustment, you have to have your equipment calibrated. After all this, we need a calibration point and then measuring series. Suppose a pressure dial gauge, you have to divide it scale in 10 pressure points. Increasing, decreasing is the measurement cycle. Then instrument properties, there are several properties. Linearity of the instrument, stability, short-term stability and long-term stability, response time of basically in precision digital transducers. Then we need precision and hysteresis of the equipment, all mechanical equipment. Reference level, when you are calibrating two pressure equipment, you need to correct the reference level of both the instrument. standards. So there is a hierarchy of standard that is agreed unit. Some of these are artifact in kilogram, some are realized, for example, in temperature. At the hierarchy are primary standard. So a measuring instrument of an apparatus which define, represent, physically observe, reproduce the unit of measurement of a quantity in order to translate to other measuring instrument is called measurement standard. Traceability, it is the unbroken chain of calibration verification from primary standard to device. But this main chain may have one link or several depending upon the value. Each stage must be fully documented. Now this slide you can clearly see the linearity of the RTD. So opposite are the plots of true value, probe temperature of one temperature probe. Note they are all approximately linear response. They each have a slightly different line. So this line is there is not much different changes, but there is lower plot. There is a big change with the temperature rise. So linearity is there, but their behavior is slightly different. Similarly, stability. With the time, you can see this these two graphs, a humidity probe. With time, their behavior is slightly moved away. Precision. Now you see this is two probes. This lower probe has a better precision, but probe 2 has some scattering more. Now, if you see this particular graph, in mechanical equipment, when you go by the increasing order of pressure, then you come decreasing order of pressure. So there is some value difference, and that differential is normally called hysteresis. And this hysteresis is determined using some mathematical formulae, and you have to take into consideration this hysteresis value. So this is the difference between linearity and hysteresis. Now, another important thing is error and blunders. So errors are happened. You see, humans are prone to errors, but blunders should always be avoided. And by definition, most measurements will not exactly right. There will be error in some degree. So a blunder is when a human make mistake. For example, he has taken a measurement by thermometer, and value is 35.25 degree, but he is writing in notebook 25.2.5. So this is blunder. Once blunder is done, it is reflected all over. So you have to keep this in mind. Now, how to improve the data quality? It is very, very important. So data quality is improved through training. So that's why most of you are here for this purpose of training. Always make your value double check. So avoid the blunder. So if you have written wrongly 25.25, but when you repeat the measurement, you will see that you have made blunder in writing. So that blunder you can avoid by repeating the measurement. Use calibrated equipment always. Minimize the number of variables as much as possible. Use standard test procedure. And if it is not broken, don't fix it. So, and after all, this is the Mool mantra of quality system. Document, document, document. Whatever you are following, you document, and what is documented, you follow it. This is the Mool mantra of quality system. So now, after this introductory of beautiful document of vocabulary of uh, terminology in metrology, now I come to the some historical background. Metrology is basically science of measurement, and if we go back to our time, you will see the people were trying to live in the caves, and unknowingly they were making measurement. But that measurement, you cannot say that they were used to it in a systematic way. Means it was not organized. If you go with prehistoric, people don't have time to measure, but over time people are trying to measure, and they started growing cattle. They started crops, and when there are crops, then they used to have growing crops in a systematic line or systematic way. So that's with some unorganized metrology they were doing. And the most beautiful example of this metrology is this Egyptian pyramid. And then slowly, if these measurements would not have been there, so this mayhem, this dhakka mukti would have been started in distributing and all this, so many things. So this resulted into our modern day metrology. So if you see this particular side from left hand side, you will find this Egyptian cubit road in their Liverpool World Museum. This was the length measurement, and in time, if you go by our Hindu mythology, you will see the cycle of Brahma, and then a day of Brahma, Mano, Manvantra, Mahayug, year, and then Kal, Paks, Ghati, Pal, Parmanu, Truti. These were the measurement being used in time. And in the length, you will find different old one in inch, foot, yard, mile, and then they came into the furlong, chain, road, 1 hand, mile. So these were the units used. Another example in India is this Emperor Jahangir, which used to have one balance, and normally they used to weigh the good work by putting some important person in one pan of the balance, and then another pan they used to have some metallic coins or this jewelry and all this. So this way, the metric system started in 1799, and the American system, Stangewind system, all this slight introduction for you people. So calibration, a little bit I made. Now, what is meteorologist? And this always we work in a important triangles. And if meteorology point of view, this triangle is very important at the grassroots level. We have the calibration technician, operators of the equipment, and to train them, we have the calibration engineer, scientists, and technical officer, and all these trained people, accreditation staff, quality expert, and at the top we have the meteorologists. We do the fundamental meteorology, which meteorology is transmitted from top to grassroots level. How we can make a good meteorologist? interested in metrology, we need to have some knowledge of these subjects. I will not say you have to have always expert in all the field, but you have to have some elementary knowledge of physical science, means physics or material properties. Mathematics, you need to have a formula and statistical analysis, uncertainty evaluation. For computer science, you need automation, programming, databasing, calculation, interpretation. And then writing skills, you must have for writing your technical documents, your research paper, your management system. So that way, when people have this elementary knowledge with expert knowledge in one of the parameter, they can become metrologist. And metrology influences, drive and underpin much what we experience our daily life: industry, trade, regulation, legislation, quality of life, science, innovation, all rely in good measurements. So metrologists, what does metrology does? It design and run measurement, calibration and test, analyze the results, determine the final accuracy of the device under test. So after all this, this particular slide, though I have covered, but if you see this accuracy definition, you have to use this equation. Basically, it is you have to have the repeatability, which is determined from the standard deviation, and then gauge reading minus standard reading whole square. Normally, people do this RG minus RS square divided by 100, but actual definition, we should also use repeatability of the measurement. This slide I have already covered, but if you want to have this zero error, this is zero error, which is altogether same, and then span error, which increases with range, and this is a linearity error. This measurement standard, I have explained. International standard is recognized by international agreement as the basis for fixing the value. And then we have the national standard, a standard recognized by national decision. Ashutosh ji is custodian of that particular thing. A standard recognized by national decision as the basis for fixing the value in a country of all other standards for a given quantity. Primary standard, which NPL is a custodian, a standard of quantity which has been realized in terms of fundamental units of mass, length, and all this. Secondary standards are traceable to nationalist primary standards. And then we have the reference standard, a standard which is the best available at the location is called reference standard. You can have your primary standard in terms of fundamental unit, but you cannot call it as national standard. It will be your national standard. So the best standard available at your location. Working standard is normally you do for the routine work. Transfer standard is used for the comparing the several standards. And traveling standard, when transfer standard goes from one place to another place for the measurement, it is the traveling standard. These are some of the important document for this pressure metrology. One is OML R101 for the pressure gauge, vacuum gauge, and other elastic element. Then we are R109 for the elastic sensing element and vacuum gauges. And R53, though it is very old, some new standard is coming, elastic sensing element of measurement of pressure. And then we have tire pressure gauge for motor vehicle R23. And then pressure balances or deadweight tester, we have R110. And then we have European guidelines. You can have for the pressure balances, they have gone for this EL G26 in 2017. And that's the same guide for this Euromed for the electromechanical transducer. They have used CG17. Then for the pressure balance is CG23 for Euroman. And there is one guide by New Zealand published in 2016, technical guide 13 for pressure dial gauge. And similarly for the deadweight tester, they have technical guide 16. So these two documents from New Zealand. And for the expression of uncertainty, the latest document 2008 GUM document, which is adopted as JCGM 100. OIML G adopted by OIML G100. Then we have a sphygmomanometer for blood pressure R16 and then non-invasive automated R16 2. So this is what this particular lecture is finished. If anyone have a question related to this, I can answer. Ashutosh, if terminology lecture is finished from my side. आवाज नहीं आ रहा, मुझे तो आवाज नहीं आ रहा. आशुतोष जी, is there anyone here?
Yes, sir.
आवाज नहीं आ रहा. किसी को कोई सवाल है तो, नहीं तो मैं दूसरे लेक्चर पे जाऊं.
अभी एक क्वेश्चन है, इसमें पूछा गया है हाउ टू कैलकुलेट लीनियरिटी.
लीनियर की कैलकुलेशन के लिए लीनियर फिटिंग करते हैं हम लोग. फिटिंग करते हैं.
एक सर सेकंड क्वेश्चन पूछा गया है व्हाट इज द डिफरेंस बिटवीन रिपीटेबिलिटी एंड रिप्रोडक्टिबिलिटी.
Repeatability and reproducibility, basic difference here. Reproducibility of the measurement is by measurement can be performed on a transfer standard at different locations, different operators, maybe different method or same method at different time. Okay, and repeatability is by the same operator on a same measuring instrument under identical conditions.
सर क्वेश्चन पूछा गया है एनी मेजरमेंट ऑफ इलेक्ट्रॉनिक डिवाइस लाइक लैपटॉप. एनी मेजरमेंट ऑफ इलेक्ट्रॉनिक डिवाइस लाइक लैपटॉप.
लैपटॉप का क्या? सवाल पूरा नहीं है.
टू कैलकुलेट हाइस्ट्रेक्स.
आवाज नहीं
आ
है.
रही है कि नहीं आ रही इसमें? मेरी आवाज आ रही है?
Another question is that, yeah, where can we see the allowed limits of error for weighing valence as per weights?
नहीं आ रही आवाज.
Am I audible, sir?
बीच बीच में कट जाता है, पूरी बात नहीं सुनती.
हाँ, where can we see the allowed limit of error for weighing valence as per weights?
OML documents. You can see the OML documents. Today I am not covering the weighing balance because I was asked for the pressure gauge. That's why I included all the documents related to pressure metrology.
एक सर है हाउ टू कैलिब्रेट टन यूनिट्स प्रेशर गेज बाय यूजिंग इट्स डाया.
I will come calibration part in my different lectures today. This was related to German terminology. If there is question, I will reply.
Sir, there are some other questions. Sir, they are asking about the importance of uncertainty.
So I will say any equipment is measured, the value without uncertainty is useless. I will say because because every measurement has the dispersion in value. So until unless you tell the measurement dispersion, so this measurement value is useless. So that's why I will say uncertainty is very, very important in any measurements related to any field you go. Human health, your living standards, your petrol pump, your daily market, your clothes marking, anywhere you go. So uncertainty is very, very important. One example, if there is a little bit 10 milliliter of error in your dispensing unit, so you will see how much huge loss you will have when you have 100 liter of petrol. So 1 liter, it is very small, but when it goes to the your vehicle, it is big, and when it goes to the whole city, it is too much big. And for similarly for the country, this notional loss is enormous, huge.
Yes,
So
sir.
uncertainty, once is wrong, it reflected all over wherever this measurement is being transferred.
Yes,
So
sir.
whenever a measurement is being transferred to welfare of others, you have to have the measurement uncertainty with the value.
Thank you. Thank you very much, sir. Now, sir, my request is you please continue and we will take the questions in the end of the session.
So shall we go next
Please,
lecture?
please, sir, please. Please.
So this particular lecture, I will be speaking about this fitting and accessories generally used in pressure metrology, because whenever you are making your measurement setup, these equipment and accessories are very, very important. You must understand the implications and their characteristic correctly. So your measurement setup is made absolute. This I don't know. Let me give slightly one or two. Lord Kelvin said that when you can measure what you are speaking about and express it in number, you can know something about it. But if you cannot measure it, if you cannot improve you cannot improve it. So this was the Lord Kelvin. And similar, Albert Einstein, a pretty experiment is it in itself often more valuable than 20 formulae extracted from the minds. So what he was saying, theoretical values you can have many, theoretical concept, but one experiment is better than 1,000 opinions. Similarly, these are a few examples. I will not waste the time. This was slide made for some other purpose. So I will come to the fitting part. So we have in fitting, we have pneumatic and hydraulic experimental setup. So in pneumatic, you have the study of mechanical properties of gases, and gases can be compressed and stored from potential energy. And in hydraulic is the study of fluid mechanics. Liquid cannot be compressed, so they are well suited to perform heavily loaded tasks at a distance when gases would just further compress. So that's why this hydraulic systems are more often favored. So pressure fitting and system assembly, the choice of fittings and tubing which are used to interconnect the pressure balancing and the test instrument directed by several factors. Most important is the system is safe at the maximum pressure condition. You have to have this, because this is a safety of the operator and safety of the surrounding is very, very important. Safety of the instrument. It is best to use the largest fork compatible with safe operation at the highest system pressure. You use as much as possible big bore tubing. The tubing should be as short as possible to minimize system volume, because to minimize the energy stored in the system and to reduce the response time. If your circuit is longer, your response time or sensitivity will be affected. So these are some tubing fitting and the sizes of tube with respect to pressure range. If you are using in a lower pressure, you can use copper, plastic, and rubber tubing. Up to 4 megapascal, you can use copper tubing, and above then you can use stainless steel tubing up to 100 megapascal. 400 megapascal, another fitting type. This Amnicol or Nova. 700 you can use composite, and above 700 you can use composite materials. These are some of the important companies, but I am not promoting the companies here. My job is only to make you aware. So please understand this clearly. I am not promoting any company. So you are the better judge, but I have said here about the scale and suitable fittings. When you are going for the hydraulic oil systems, you have to use these oil systems are very, very useful. 2-ethyl diethyl hexaicate, popularly known as Sibacate, you can use from atmosphere to 5 gigapascal. But SAE 10, 20, 30, and 40 heavy duty motor oil available at petrol pump, instrument oil, spindle oil, turbine oil, caster 30, 40 motor oil. These are easily available. You can use up to 300 megapascal depending upon the viscosity. And then above 300, you can use Versol pure white gasoline up to 800 megapascal. Then we have octane and Plaxone mixture, heptane mixture of 1500 megapascal. And above that, you can have white gasoline, Plaxol, isothermal alcohol, and pentane mixture, 3 gigapascal pentane mixture. For the this much high pressure oil companies, this slide is very, very, very important. When we come to the typical materials for the construction and range of board and gauges, you must understand what is intrinsic property of board and gauges. Phosphor bronze are there, beryllium copper, alloy steel, carbon steel, stainless steel, and other nickel span type. So these are the ranges, like for example, phosphor bronze gauges are used up to 1000 psi, and similarly this carbon steel up to 500 psi, and the other 20,000 psi, and all these gauges you can use. When you go for the surface tension of liquid, normally these fluids pressure equation surface tension value is used. So these value you can use. These are collected from the prominent literature values. So these value can be used for. These are the thermal expansion coefficient of piston cylinder assembly applied in pressure correction. Different value. Normally, tungsten carbide and stainless steel are used in dead weight tester, but sometimes other materials are being used. This is piston cylinder material. Again, some material. Cohesion ratio. Now you see this important function is needle valve. Most of the time in pressure circuit, you have to have a two-way needle valve. You can see the intrinsic property. This type of needle valve you can use up to 7,000 bar. Again, different type of two-way. This is L-type needle valve. This is a three-way needle valve. Again, L-type, and again two-way, different. One way you can pass, one way you can close. So this way you can use this type of needle valves. We'll give two examples of these needle valves. Then we have the compressor. So until and unless you compress the liquid, you cannot generate pressure. To generate pressure, you need a screw mechanism pump. So these hydraulic pumps are available. So the main feature should be non-rotating spindle for longer packing life, easy retightening the seal, independent operation without electrical or pneumatic power system, and three large handle for easy operation. So these are some of the characteristics to generating. Then we have several small setup on a single bench. So you can make such a single bench which you can take into the field for the field calibration. Very, very simple. You can have reservoir, you can have one pump, and then you can have needle valve and a test gauge and standard gauge. So a very simple experiment for your field experiments. Screw pump intrinsic properties, pressure tubing, different size. These are the characteristic of different size tubing. Then we have the elbow T connection, and then multi connection means cross. You can have a different type of these designs in your joint of your joining your systems. Specifications, and then we have sometimes you have a bigger pipe, and then you have to connect to your standard with lower tube size, so you have to use a reducer. So these are some good quality reducer in quarter-inch size. Nipples, gland, ferrules. These are very, very useful for stopping leakages. This is a dummy plug. Sometimes you have to make one of the connection a dummy. And then flexible hose pipes and different designs. Then we have a reference pressure monitor. Again, I am not promoting any company. Just I am saying that you need to have a reference monitor. Then we have in between a constant volume valve, and for measuring temperature, you need some multimeter, and then humidity and temperature, you need environment condition monitoring systems. Then you need this tooling for making threading in your tubing. And this slide I have already shown you standards. So this is our Ashutosh, this is our second lecture. I hope this teaching lecture is also very, very important.
Yes, sir. Thank you very much, sir. Thank you. It is very important that how we are doing it. But basically, this is very important. Until we don't know what is the pressure of the liquid, how much pressure we, or how we can generate the pressure, how we can sustain the pressure, how we can reduce the pressure. It is very important. I think many of us are not aware about this basic technology behind this pressure measurements. It is very important, and I hope, sir, that we must be needing some more lectures on these individual parts, so that you can explain us how you are doing actually in the field. I would say my request is in the next time or very soon when we will be having a lecture. Actually, I unfortunately I could not spoke to you. Yes, I wanted to request you kindly give some videos, small videos if you have, so that we can share it with the help of NPL. It will be very good to understand how you people are actually doing the calibration and the testing.
Maybe
Next time, sir, certainly I will help you.
Maybe next time I will show video. I think I don't have this time, and if it is available in my folder, I will definitely see. So
Very good. So next time, actually we want to see how you are doing in your lab, how you are calculating the uncertainty, and would like to request you to kindly give us the uncertainty calculation sheets, calculation sheet, Excel sheets, etc., so that the participants of the whole over the country, they have a uniform structure. How to calculate the uncertainty. There should not be any event, but it is a simple procedure you have to follow. This we would like to request you. We will do it, sir, next time. I hope this time it is very important that theoretically we are understanding what is pressure measurements. It is very good, sir. My request is you please continue. Otherwise, I understand if we will take the questions in during these questions, we will miss the.
I will go to my next, sir.
Please, sir. But if you want to reply, sir, there is one small question. What is used ISO standard calibration of ton unit pressure gauge calibration?
ISO का तो अभी कोई प्रेशर गेज पे स्टैंडर्ड नहीं है। जो स्टैंडर्ड मैंने यहाँ पे आपको दिखाए हैं वो ही इम्पोर्टेंट स्टैंडर्ड है।
OML और ये आप यूरोमेट यही है। ठीक है सर, प्लीज सर काइंडली कंटिन्यू।
I think if I should left this. Maybe sometimes I will show. Go over the next lecture as you suggested.
Please,
I
sir.
will go for the calibration part.
Yes, sir. Please.
So I will come to the now this pressure calibration. So when you are performing pressure calibration, you need to identify all the influencing quantity and what should we identify. Certainly, what affects the pressure measurement. What do we have to identify? Number one, everything that can impact our measurement. So those measurement which are at the environmental condition level, you have to have local gravity, ambient air temperature in the room, barometric pressure, electrostatic charges, magnetic effect, housekeeping, vibration, humidity in the prevailing in the room. Then second one is characteristic related to bench stability. These are the bench level requirement. Bench stability, leak in the system, deformation of tube. If there is several deformation tube, it will affect level of precision, level of instrument, changing fluid density, fluid contamination when you are connecting customer gauge, the different fluid in your customer and different fluid in your standard. This will make contamination, calibration, procedure, fluid head corrections, cylindrical piston installed, piston cleanliness, piston drive, and piston rotation. Then we have some of the requirement at the operator level. The operator's formal training. He should know exactly what is mass accounting. The habits of the operator are very, very important. They should not use alcohols and performing measurements. Certainly, it will affect all the measurements. Level of precision is another important. And then we have a few requirement at the calculation level. So, what are those pressure equation? What are the error? What are the conversion factors? Rounding error, apparent and true mass, and then assumption and interpretation of the results. These are the operator level requirements. So, what is calibration? This definition I have already explained. Traceability is a concept to establish a valid calibration of a measuring instrument or a measuring standard by a step-by-step comparison with better working national or international standards. So these 5W we have to remember. So one W is what is calibration. Another is who can perform calibration. So who can perform? Any well-qualified operator, maybe technician, engineer, scientist who is well familiar with the calibration procedure, measuring instrument, calibration setup, apparatus, measuring principle, data analysis, interpretation, computation in a national laboratory, accredited calibration laboratory, in-house industrial calibration laboratory, etc. Third W is why calibration is required. To know the operational integrity of any instrument, you need calibration against the standard. And another W is when calibration is required, very, very important. When calibration is required, any new instrument required calibration. Deviation of measuring data from past, if you observe your data is deviating from previous data, then you have to check recalibration instrument. If instrument is repair, service, adjusted, you have to get it calibrated. And fourth one, whenever legal authority advises, legal authority, I mean to say your accreditation authority also, your legal metrology department also, any legal authority advises you go for the calibration, you have to go for the calibration. Initial stages, one can go for calibration of measuring instrument at regular interval until the history of the gauge behavior is not known. If user know the history of the gauge behavior, measurement data, condition of the use of frequency, means measurement are performed in laboratory or measurement performed in workshop. So this type of condition you have to remember. He can himself decide the duration of the next calibration, because ISO 17025 itself says that it is user dependent. Already one document is published by OIML. I think D8 or something, मुझे exact याद नहीं, D8 probably Ashutosh ji might be remembering. This calibration interval is clearly mentioned there. All conditions. It's a small document, maybe 5-6 pages. Then another was how to do calibration. So how to do calibration? You need to have inspection of the customer requirement, and this particular slide will also help you to make your calibration procedure or your thing. If you make your requirement on these points, you can easily make your calibration procedure. So foremost thing is you have to verify the customer requirement when instrument comes. Inspection of the test instrument, it can be visual inspection, it can be preliminary check, determination of meteorological characteristic, then verification of availability of necessary material To calibrate this equipment means you have the adapter, transmitting fluid, cleaning agent, tissue paper like you must have all these. Then preparation of calibration setup. मैंने पिछली स्लाइड में जो फिटिंग दिखाया है वो सारी चीजें आपका तैयार हैं तो आप कैलिब्रेशन सेटअप लगाइए. Then leveling of and zero setting of instrument. Then we have the calibration method. In pressure metrology, you have to have these calibration methods. One is cross floating of dead weight tester. One method is this. Another is calibration of pressure dial gauge against dead weight tester. Third one is calibration of pressure dial gauge against dead weight tester. One is transducer, one is dial gauge. Third one is calibration of dial gauge against pressure transducer, and fourth one is calibration of dial gauge against pressure dial gauge. Please remember, you cannot calibrate equipment of a better quality with lower accuracy equipment. Means you cannot calibrate dial gauge against pressure transducer of high accuracy against the dial gauge. So please remember, I have seen a few people, they were calibrating a dead weight tester against dial gauge. So this is very, very important. So your equipment must be higher. Data collection and recording, then data analysis and computation, and finally presentation of calibration result is another important. You have to have all this information in presentation of calibration result, means the name and address of both the calibration authority and the owner of the test gauge, calibration party, reference number, serial number, model, manufacturer, environmental conditions, name, measurement, uncertainty, and traceability of the standard. Then briefly methodology, and then calibration data, uncertainty statement of the calibration, and then measurement period, unique calibration report number, and suggested next calibration due. You cannot force due date on the user. You have to suggest the next calibration due date only. Ashutosh ji can force next calibration date. Now we can go for the calibration of dead weight tester to dead weight tester. You have to install this equipment. This is in middle you can see the standard dead weight tester, and right hand side you can see the test instrument or customer dead weight tester. So when we are measuring, I said you have to have the level difference. So level difference is determined from the bottom of the piston. Generally, this reference plane is marked on the dead weight testers, and in between we can use constant volume valve. So generally people ask, is it necessary to use constant volume valve? In my opinion, it is not mandatory, but constant volume valve is a very, very essential equipment to make your calibration procedure smooth and proper and timely. For example, you have make this test gauge instrument at the reference plane, and then you stop the constant volume valve, then make a reference standard at the reference plane, and then close the needle valve, and then you see both dead weight tester are operating at the reference plane. But moment you open the constant valve, immediately you will find that which pressure standard is heavier and which one is lighter. So you can adjust the mass on the standard and determine the exact pressure value. So this is the simple calibration procedure by this experimental setup. So one slightly animation of this you can see. You can apply pressure from this to lift the piston at the reference plane. And then this pressure is transmitted to the pressure dial gauge. and then you can discharge if required. This is a pump design. And now this next setup is when you are calibrating pressure transducer against deadweight tester. You have to apply this experimental setup. Here constant volume value is not required. Constant volume value is normally required in deadweight to deadweight tester. So for calibrating deadweight tester, you need to have in terms of output, in terms of frequency, in terms of voltage, or any other capacitance type, then you need to have a power supply. All this you have to install. And then for the reference plane, generally, if there is no marking on the reference plane of the transducer, you can take this is a convention to take the central part of the transducer as a reference plane and bottom of the piston at the reference standard. So this way you can calibrate transducer. And transducer calibration can be made by two ways. One method is just putting a mass on the standard and see the measurement reading on the transducer. Another method is you adjust the mass on the deadweight tester according to the fixed value of the transducer. The fixed value of the transducer is very, very difficult in digital gauges because Boyle's law, this pressure relationship with temperature and volume change, the stability of the transducer reading is very, very difficult. So personally, I always recommend you put pressure mass, some fixed mass at the deadweight tester and see the transducer reading. And then on the same masses, you take the repeated measurement at the transducer with varying environmental condition, and then make the fitting of the data to see the behavior of the gauge. So that way, this method is very, very good. But I am not stopping you by another method also using, if you can fix the value of the transducer, but it is very, very difficult. Third experiment, yes, I just told you the linear fitting is required in deadweight tester calibration also, and in transducer calibration also. So this particular equation you can use. This is equation is very simple equation. Y is equal to mx plus c. So this is this component is mx. This is c, and this is y, corrected value. So how to determine these value from the data? You can determine this delta p using this equation, and standard deviation, this slope using this equation, and this intercept by using this equation, and standard deviation by y minus using this equation, and you can make a small Excel sheet putting x and y value, and simply you can determine these value, and it's a very, very simple method. When you are using calibration deadweight to deadweight tester, you have to make model equation. Test gauge is equal to mean pressure on the standard deadweight tester plus delta P is the error. When you differentiate this equation, you can find this equation, and using this sensitivity coefficient, you can determine the exact uncertainty value of this equation. And for linear fitting equation, I have already explained in previous slide. This is not so important. Hydraulic pressure gauge. Okay. Now come to the another calibration of dial gauge. In place of pressure transducer and transmitter, you can remove this portion and you can remove, you can connect dial gauge. So both way you can use same setup and you can connect your dial gauge. But when you are using pressure gauge against dial gauge, this pressure transducer, this portion will come in place of dead weight tester. So simple this line diagram, I have put all the possible calibration method. So effect of environmental conditions. So location of pressure balance should be free from drought as much as possible. Stable temperature conditions are necessary to ensure that temperature of the piston cylinder assembly is uniform. Temperature of the piston assembly must always be measured during the operation so that appropriate correction of any variation of the reference temperature. Ambient temperature within plus minus 20, 15 and 25 degrees centigrade with stability plus minus 2 degrees centigrade. This is a standard document OML. Lower uncertainty, typically value 0.01% at the temperature of PCA. Relative humidity between 40 and 65. Control opening of doors and movement of operator to keep stable atmosphere. Control ventilation in order to prevent intense airflow. Pressure fitting I have covered. This I have covered. Choice of fluid I have covered. This slide I have covered. Leveling. To ensure that axis of piston cylinder assembly is vertical, leveling is normally facilitated by adjustable feet. It is advisable to level the instrument with reference to the plane piston cylinder unit itself. For top loading piston, leveling may be done by placing a split level. For the overhang type piston, leveling may be carried out at the hanger level. Cleanliness. How to clean the piston and cylinder? It should be ensured that solvent dissolve the operating fluid, remove dirt, does not attack the piston cylinder surface, and does not have a residue on the surfaces. Place each beaker into an ultrasonic bath if possible, if you have the facility, and clean for several minutes if possible. The working surface of the piston should not be touched by hand. Otherwise, skin impression or grease on the hands line may contaminate. If an ultrasonic bath is not available, use laboratory grade tissue papers such as lens tissue paper are very essential. Soaked in this solvent, you can clean piston and cylinder. In the oil case, a thin film should always be applied when you are keeping piston and cylinder. Dry all parts using clean gas or air. And then for oil operated units, both surfaces in oil. Fluid system, okay. Pressure measurement done. Device installation I have mentioned. For gas pressure, liquid. Now, for the methodology inspection of a this I will explain, I think it's not necessary. Hardware, electrical, chemical, which are very important in the laboratory. Hardware, you can have adapter, O-ring, gland nut, sleeve, pressure tubing, and then electrical, you must have this test gauge connection point before half an hour. Chemicals, you must have cleaning agent, acetone, methanol, ethanol, tissue papers, diethyl hexyl silicate, spinostic, means transmitting fluid. Measurement procedure. First of all, full pressure you have to apply to the dial gauge. Normally, we calibrate 10 equal pressure points. By pressurizing system, that this methodology I have explained in the figure earlier, but this is the equation, summation or mass, and this is the air buoyancy correction, surface tension correction, and denominator is area connection. When your piston A naught is at atmospheric pressure, and this is the distortion correction. B is the piston distortion, and this is the thermal expansion of piston and cylinder. And T is the reference temperature at which A naught is defined, and T is the measurement temperature. You can make all this measurement. And this delta P, how to calculate? Rho F is the fluid density minus rho air. So basically this is very dominant in hydraulic, because rho air is around 1, and but fluid density is around 900. So when 900 minus 1 is again equivalent to 900, so this will make a big difference in hydraulic. But in pneumatic, any gas must also be having around 1. 1 minus 1, it is negligible. So that way this correction is sometimes avoidable in gases, but in hydraulic this should not be avoided. This is the data sheet you must use in your calibration procedure, because sometimes when you perform the calibration and sometimes calculation is done little bit later, so you can have all the information at the time of calibration, what the room temperature was at the time of measurement. So you will avoid all the blunder in your measurement when you are using such type of this data sheet in your measurement. These points are increasing order, then wait for 10 minutes, and then you can start in decreasing order. So when you are taking measurement in decreasing order, if anything is written by the operator in here in increasing order, so that blunder will not repeat here. So we have itself avoided blunder in this data sheet itself. So these are the equation for the air density calculation in the calibration room. This is very, very important equation you can use. This equation is recommended by CIPM in 1981. Some small corrections have been made recently, and this equation is used in NIST by BINS. I have compared both, not much of a difference in both the values coming. Then acceleration of gravity. In your laboratory, normally you do not have the experimental value, and sometimes you have to use this theoretical value of acceleration of gravity. There is one equation recommended by this International Association of Geodesy, reference Key and Levy. You can use this uncertain value within the uncertainty of 100 ppm. Another equation is I missed here, is a British equation, but when we use both British and this American equation, I have calculated and compared with the measured value at NPL, you will find the agreement between British equation and American equation is 26 ppm, but agreement between British and measured value is 25 ppm. So this British equation is much closer to our experimental value, and similarly this American equation and measured value is 50 ppm. So at a different location at NPL we have measured the G value, and you will find that in different rooms, and if you see the C height, slight difference in C height, and you will find there is a difference of G value, and this difference of G value, if we make in ppm level, is given in the last column. So this pressure value is changed this much by this reference value. So for high precision value, this is important correction, but for low accuracy, you can use theoretical value. Similarly, when you have to make a temperature correction on the measured value, because the pressure value given in the calibration certificate at NPL is at 23 degrees centigrade, and you are using in your laboratory. So you have to convert that value in your local temperature. So you can use this equation. Similarly, in ambient temperature value, you can use piston cylinder this value correction. And when these gravity correction and temperature, piston cylinder assembly and head correction and air density correction are applied, you see, I have made these values and quantum of the correction for your reference. This slide is used here. But if you see, if you use measured value in place of a manufacturer G value, you see you are itself is giving around 0.2% error in your result. So please remember, pressure value is G dependent. Similarly, in temperature correction, you can have 3-degree difference of temperature. You can have around 30 ppm difference. In head correction, you can see change in pressure value 10, 20, 30, and then you can have these small changes in the pressure value. Each correction I have explained earlier. So uncertainty calculation is simple. Apply a head correction and temperature correction and G correction. You make all the measurement at one temperature and at one G, and then make repeated measurements, and then determine the suppose number of 6 observation, determine the mean value, and then determine the standard deviation. The square of you can determine the x minus x bar, means you minus the standard this mean value from the individual value, and then make summation, and then divide it by n minus 1. You can determine the sigma or this standard deviation. Or standard deviation is when divided by root n gives the type A uncertainty. And then degree of freedom, simply you can use this equation I have given in my last slide. And then final combined uncertainty. And this is the uncertainty budget. You can calculate and report. Linear equation I have covered. This is the example in Excel sheet I have prepared for you people. You can use such a simple Excel sheet. For example, these are the weights on the deadweight tester: 24, 26, 27. 27 is the piston and hanger mass, and 24 and 26 are individually placed. Here are the corresponding mass value, and then you make summation here. And with respect to repeated measurement of temperature, this small fraction is adjusted on the deadweight tester in grams or milligrams, and then you make the total mass. Total mass is for individual 6 reading is here. Then you multiply by G value, M into local G value, and then you can make multiply by air buoyancy correction. Then gamma C you can add. So your numerator is now determined, which is called a force on the piston. And for the numerator, first you have to determine the nominal value. Because if you see the equation, 1 plus BP, A naught multiplied by 1 plus BP. So here itself P is coming, and in left hand side of the equation P is coming. So this P is basically nominal value. Normally people make mistake here because they do not understand what is this 1 plus BP. So this P is correction, the pressure value before correction, means it is the force divided by A naught only. Then we have to determine 1 plus BP. This is normally around unity. If temperature is more, it will be coming in plus. Temperature is less, it will coming in 0.999. So similarly, after temperature correction, area correction, you can determine the area value, and then force divided by area, you can determine the pressure value. Then you can convert in your desired pressure unit, unit, and then make correction. Like I have converted pressure into PSI. So after all this correction, you have to make the temperature correction. I have shown in my one of the slide at 23 degrees centigrade. Then it manufacturer G value correction. So then ultimately this is the last corrected value with a nominal pressure of 200 bar, and then your value, this is mean value. Then here this is the deviation. Deviation is square, standard deviation you can determine, and divided by root n you can determine the type A uncertainty. And by you can take the largest type A uncertainty, and you can make then combine uncertainty using standard uncertainty, and you can take the uncertainty budget. Similarly, in dial gauge, this example is given. I suppose by using the last slide, you have determined the pressure corrected value. This is the nominal value, and this is the mean value, and then sigma, and then type A uncertainty, and then mean value minus this sigma. You can determine the delta P. This is as per 141 guide. And the different pressure point, it is repeated, and after this you have to make linear square fitting. This Excel sheet is prepared for you people only. Here is the x value, here is the correction value. You can make xy, you can make x square, and then using those equations you can make delta P0 S and then correction value. And after all this you can make uncertainty of these slope and intercept, and then determine the exact uncertainty value. And this mathematical modeling is for effective area. Sometimes other times I can cover, because now time is over. Other topic I will be taking later on. This is for uncertainty value of that. So thank you very much, Ashutosh ji.
Thank you very much, sir. You have explained a lot of things. But again, I would like to request you, sir, kindly give us some videos or show us some videos,
Next
or
time,
kindly
sir,
take us in the laboratory.
I
Yes,
will not.
sir.
Let me check one or two if available here.
Please, sir, please. Please, it will be very good help. But sir, some of them are asking that which standard they should use for pressure gauge.
Pressure gauge, I have given in my slide. You can use any of those standards. All are recommended standards. And
Because
normally people are following DKD 6.
yes, DKD, I think DKD R61 is also recommended by NABL.
Yeah, but most of the time, these standards are internationally accepted.
Okay, sir. Okay.
Sir, unfortunately, nothing is there. I have
No problem,
which folder I have put. Next time I will place.
Please, sir. Please.
Not in for this folder. Sorry.
No problem, sir. Sir, the question is how to define the accuracy of the pressure gauges in industrial purpose.
In
For industrial purpose.
in industrial purpose, the DKD guide is said as per the requirement of your accuracy class. There are increasing, decreasing, and increasing. Only 3 is sufficient. And if your accuracy class allowed you, sometimes you need increasing, decreasing, increasing, decreasing. What I have said, 6 cycle, everything is coming in 6 cycle. So if you are making 6 cycle, nobody will stop you. But if your accuracy is too small, you can, because DKD guide allows you as per your accuracy class. If your requirement is 2% accuracy, I don't think you need 6 observation repeatedly. So you can go increasing, decreasing, increasing.
Good. Sir, the next question is, what is important for calibration? Accuracy or uncertainty of instrument? Basically, I think you should say uncertainty of measurement.
Metrology point of view always believe in uncertainty, not in accuracy, but for manufacturer point of view, accuracy is also important. Because I have made the basic difference between accuracy and uncertainty. Accuracy is the characteristic of the instrument, and uncertainty is the characteristic of the measurement. Your equipment is more precise than your accuracy, because it depends upon how the manufacturer has assigned the nominal value. Suppose your dial gauge is assigned at 10 and your repeated measurements are coming at 9.5. So it is not fault of the instrument. It is fault of the manufacturer in assigning the value. So my answer is diplomatic. For the manufacturer point of view, accuracy is also important. For the metrology point of view, uncertainty is highly important.
Thank you, sir. Sir, the next question is, what is the difference between measurement and testing? I think the right question will be, what is the difference between calibration and testing?
Normally, testing is done without uncertainty, but nowadays in testing also uncertainty part is playing. I will say testing may cover different parameter also. Testing of the equipment may have different parameter, means temperature all together. But in calibration, you can have even parametric calibration in repeated conditions. So calibration is a very, very extensive exercise, and testing in a, I will say in a lighter way. You can have for much lighter way, you can take testing, but now metrologists are taking testing also seriously. So in testing also uncertainty is introduced. So when uncertainty is introduced, it means you have to make repeated measurements. Sometimes people confuse between verification and testing. Verification is normally to understand the tolerances, how much specification within a specification it is coming. But and people were using testing also for this purpose. But when this uncertainty is coming into picture, the gap between calibration and testing is smaller.
Okay, thank you, sir. Sir, another question is, CMC of instrument depends on what? Accuracy or uncertainty?
CMC
is uncertainty.
It's basically uncertainty is taken, but since our accreditation authority sometimes said that you take the accuracy also into consideration, which I am not much fond of it. CMC is basically the best measurement capability at your location.
Yes, sir. Sir, one another question is, we are not using dead weight for pressure calibration. How do we calculate UNC?
We are not using dead weight tester for calibration. How to calculate the uncertainty?
Yes, sir, uncertainty.
So some instrument might be used, they are using in place of dead weight tester, maybe dead weight transducer.
Okay.
Some instrument they might be using better equipment.
Yes, sir.
So the uncertainty of the master equipment will be used as a standard. And then the procedure I have told, similar procedure you can follow.
Okay. Sir, another question is,
Here, I will show you in this slide.
Please, please. For some calibration period, actually, there is a document with ILAC and OML. We call in OML it is D10 document, and there was some agreement, yeah, long back for the this calibration period with the OML and the ILAC accreditation body, and they have given a joint document which is called OML D10, and similarly, it also has a signature of ILAC.
You can check this slide. In place of that weight tester, you can use your master equipment. And then same, the instrument is same. But my point of concern is that your standard should be at least 3 times better.
True. Sir, somebody is asking the attendance sheet. I don't know why. What you will do with the attendance sheet? Because we are issuing the certificates to all the participants, and this certificate will also issue. Actually, sir, if you kindly allow me, I want to share this presentation to the participants.
No, sir, that is not allowed.
Okay. All right, sir. Thank you. Sorry. So I will not share the participant or to the presentation participants because it is only.
Reason is simple. Some of the slide I have taken permission to use. I cannot share.
Okay, so my request is I'm not in a position to share this presentation to the participants. Whatsoever the discussion has been done, if you have, because I have taken my notes with me, and if you have also taken, it is good. Otherwise, we will again request Yadav sir to kindly come once again with some more videos, more explanation, and with the same slides. So my request is, if it is possible, we can give them some at least one Excel sheet,
sir,
or one way of.
I will give you one of my article of pressure measurement in a PDF format. You can use that.
Please, I will. You can share it so that when I will issue the certificates within a week or so, I will issue with this certificate that particular.
Problem in sharing is no problem. You must understand, because few of the slide I have used taking permission, and nowadays this is comes under the plagiarism. So if I share it, I am bound with the disclosure agreement.
Okay, no problem, sir. There is no problem at all. But my request is, you kindly share us the Excel sheets for calculation of uncertainty, measurement uncertainty.
All the gist of this talk.
Measurement uncertainty calculation.
Yes, it is there.
Okay, so sir, in the paper.
Yes, it is there.
Very good. So kindly share that one only, sir. It will serve our purpose, and so that, sir, this will certainly take our laboratories to a level where they will say that all the standards, all the calibrations, all the measurement uncertainties undertakings are the correct, and they are at par with the national standard, which is at par with the international standard. So, sir, thank you very much. I would like to thank Professor Sanjay Yadav, sir, who is here to help us to just guide us how to do the calibration, how to do the testing in the pressure. But sir, I would, because I have seen that you are sitting in the lab, but in your office, but I would like to see your laboratory next time so that you can share, or otherwise I will come to NPL next time when we will be having this program. very soon, and you kindly show with the help of this mobile video or with the help of the
We have always prepared
direct.
few videos, as I told you a few days back. So I will say that I don't know where those video have kept. I do not remember. So
No problem.
I have to put time.
Please. So, but my request is, if it is possible, you can come once again in the next week or so, whenever you have the time, and we can just see these videos so that we can understand and you can explain how we are doing. That will be better.
Certainly, certainly.
Thank you very much, sir. I would like to thank you because you are my one of the best friend, and secondly, you are having. I am actually privileged to have you with us, and certainly it is my always a privilege that I have a friend like you. Always very helpful, very gentle, and nice gentleman. And sir, I would like to thank our director sir, who is also always helpful. Whenever we say that, sir, kindly come, he always used to help us. And certainly all the participants, we have a large number of participants today, and maybe more than 400 plus participants we are having. And so these certainly it will help all the laboratories who are actually looking towards this pressure calibration. But I think that videos will be certainly helpful to us. With this, I would like to thank all who have joined this conference. And thank you very much, sir. We will meet again. Thank you. Thank you, sir. Thank you.